Hi, my name is Marius, and I'll be presenting my joint work with Paritosh, Verma, and our advisor Alexandros on automating food drop with the power of two choices for dynamic and fair food allocation. So, food insecurity. Food insecurity and food waste are two global pressing issues that hardly need an introduction, but let me just give you some key statistics that help highlight the importance of these problems. So, in the US alone, 30% to 40% of food is wasted, which is translated to 149 billion meals yearly. At the same time, almost paradoxically, globally in 2021, 928 million people were food insecure. And in the US, 44.2 million people lived in food insecure households in 2022. There are various organizations that try to address this problem on a local or bigger level. One of these non-profit organizations is Indie Hunger Network. And one of the projects that Indie Hunger Network has is the food drop program, which used to work as follows. You have a supermarket and a food delivery arrives, and it's rejected for reasons that have little to do with whether the food delivery is actually edible or not. So then the truck driver, what he would do would be to contact a representative of Indie Hunger Network. And then the representative will start contacting one by one the available food banks until they find a food bank that can accept this food delivery. And then they match the truck driver to the food bank. However, this procedure is quite labor intensive for the IHN representative. And at the same time, as it happens with human decision making, the decisions were very skewed. Few of the food banks took most of the available resources. So Indie Hunger Network reached out and asked us to automate their procedure. And we developed our platform. And I'm going to jump right ahead to present a typical use case of our platform that will highlight the problem we have at hand. So let's say that a food load of W pounds is rejected at point X, and the truck driver next destination is point Y. And our goal will be essentially to, in an online fashion, match the truck driver to some food bank. So once the food delivery is rejected, the truck driver will actually go into our platform. He will fill in a form with relevant information regarding his contact details, the origin and destination, estimated time of departure, and food load specifications. And here you can see actually a screenshot from the form that's being used today. And once they press submit, this will create a request to our backend, which is currently hosted in AWS. And this will initiate our dynamic fair matching algorithm, which will create a fair ordering of food banks. I will discuss later what fair means in this setting. And then it will automatically start contacting food banks one by one. And this is the interface that the food banks will see. The food banks will receive in a pre-specified phone number a text message with a link that will redirect them to a web page where they can see information regarding the food load, the time of arrival to their location, and they will have the option to accept or reject this food load. And if they reject or they don't reply within a pre-specified time period, then the next food bank is contacted until someone accepts. So finally, once some food bank accepts the food delivery, then we match the food bank to the truck driver and we exchange their information. We automatically send the information, the relevant information to the truck driver and the contact information to the food bank. So essentially the most important part of our platform is arguably our matching algorithm, which has some theoretical guarantees. But in order to prove these theoretical guarantees, we need to cast a real-life problem into a theoretical one. So we model our problem as a graph where the edges between nodes will have some distance metric that will satisfy triangle inequality. And each node is characterized by two different things. One of them is going to be the food insecure population that resides in this specific node. And the second one is going to be whether a food bank is in this node or not. In order to actually prove things that are interesting, we also have to make a few more assumptions. The first assumption is that the food insecure individuals are served by the food bank that's closest to their node. The second assumption is that once a food bank receives a food delivery, they're going to equally distribute it amongst the food insecure population that they serve. The third assumption is that the weight of the deliveries is going to be sampled IID from some well-behaved distribution. And then the fourth assumption is that the origin and destination of the food delivery is going to be sampled IID from a distribution that's close to being proportional to the food insecure population. And the rationale behind this decision is that from data we can see that the actual population, the distribution of the actual population is very close to the distribution of the food insecure population in each area. And so the more population in one specific node, the more supermarkets, the more food deliveries, and thus the more deliveries are going to be rejected. So essentially, we want to match the food deliveries to food banks in a way that is both efficient for the truck drivers and at the same time it's fair for the food insecure individuals. And towards this end, let's define delta driver efficiency, which here the D will be the distance metric on our graph. F will be the food bank that we chose to match the food delivery to. And F star is the food bank that minimizes the driving distance of the truck driver. And essentially, a delta driver efficient matching algorithm will be the one that guarantees that no truck driver will need to travel more than delta times his optimal driving distance. Now, in terms of fairness, we define epsilon multiplicatively MV freeness, where here WF of M is the weight of food donations that food bank F has received after M food deliveries have been allocated. NF is the food insecure population that food bank F serves. And essentially, a matching algorithm that's epsilon multiplicatively MV3 means that there is no individual that has received weight of food donations more than epsilon times any other individual has received. So let's talk about our results now, our theoretical results. First, let's see our lower bound. Essentially, informally, our lower bound says that there is no matching algorithm that can achieve driver efficiency strictly better than 3 and have anything reasonable in multiplicatively MV freeness, something that's better than a factor of n. And the example is quite simple, actually, that proves this theorem. Consider the following graph, where in nodes V1 through Vn, there is one food insecure individual that resides. And in nodes AB, we have 0. In the red nodes, we're going to have food banks. And in the black ones, we don't. And if you look at the distances, the important thing is that the food insecure individual that resides in node V1 is going to be served by food bank in node A. And when a food delivery arrives, in order to be strictly better than 3 driver efficient, the only way that we can allocate the food delivery to food bank A is if both the origin and the destination are sampled to be at node V1, which happens with probability 1 over n squared. However, food bank A should have received 1 over n of the food deliveries. And this essentially proves that even if in the offline problem, this lower bound still holds. Now let's see our algorithm. It's fairly simple. First, find the food bank that's closest to the origin of the food delivery. Then find the food bank that's closest to the destination and match the food delivery to the food bank between the two that has received the least weight of food donations per food insecure individual that they serve. And the theorem is that this specific matching algorithm is 3 driver efficient and 1 plus epsilon multiplicatively MV3, where epsilon goes to 0 as the number of food donations go to infinity, and this holds with high probability. So the 3 driver efficient is a simple application of triangle inequality in our graph. Where does our multiplicative MV freeness guarantee come from? And as the title of our paper might have already suggested, there is a connection of our problem to balanced allocations and balls into bins type of problems. So as a quick reminder, let me do a very brief introduction on this area. Suppose you have a setting where you have n bins, and let's say for now that at each round, I'm gonna sample one bin uniformly at random. And let's say I sample bin 2, and I'm gonna add a ball into the specific bin. I continue this way until I have inserted a total of m balls into the bins. Now consider a second experiment where again I have n bins, but now I sample uniformly at random 2 bins, and I'm going to insert the ball to the bin that has received the least balls up until that specific point in time. So now let's say that uniformly at random I sample bins 2 and 3. I'm going to insert the ball at bin 2 since 3 has already received one. So the theoretical question is, after I've inserted m balls, what is an upper bound on the maximum balls a bin has received with high probability? So in our first experiment, the random choice one, it's easy to prove that you won't receive more than a factor of square root m log n divided by n balls than the expected number of balls that you would have received. But in the second experiment, which is also referred to as the power of 2 choices, this dramatically improves and becomes a order of log n. And the impressive thing here is that this does not depend on the number of balls that we have actually inserted. So going back to our problem, really thinking about the problem that we have at hand, we will suddenly realize that essentially we have a problem where the donations can be considered as weighted balls. The food banks can be considered as weighted bins. And the selection probability of the bins is non-proportional to the weight of the bin. And our contribution to this line of literature is that we prove power of 2 choice style results for this exact setting and relate them to our problem. So finally, in order to robustify, let's say, our theoretical results, we also conduct some synthetic experiments where each node will be a county. We sample the distance between nodes using the ping maps API. And we sample the origin and destination of the food deliveries to be proportional to the actual population of each node. And we use the Feeding America dataset to get the information of how many food insecure individuals reside in each node and where are the location of the food banks. So we conducted the experiments on various states. Let me just show you the results for California. Our algorithm is after 50,000 food donations have been allocated, is 1.0044 multiplicatively MV3, and is 2.92 delta driver efficient. And the impressive thing here is that on average, the truck drivers didn't need to travel a distance more than 1.06 times the actual distance that they had to, which implies that on average, the guarantee for the driver efficiency is much better than what our upper bound might suggest. And also let me give you another visually appealing graph that we have. Here you can see at the first image, the distribution of food insecure individuals in California. The darker the red, the more food insecure individual in this specific county. And then in the next 3 images, you can see the performance of 3 different matching algorithms. The first one is the driver optimal matching algorithm, where every food delivery, we match it to the food bank that's going to minimize the driving distance of the truck driver. The next one is our algorithm. And the final one is something that interpolates between the driver optimal and the food bank optimal, where we essentially give each food delivery to the food bank that has received the least weight of donations per food insecure individual up until that point, with a specific cutoff that, let's say, the truck driver will not drive more than 60 miles his optimal driving distance. And here, green means that this specific county has received exactly the amount of food they should receive. Red means that they are underserved, and darker colors mean that they are overserved. And we can see that the rest, natural algorithms that one could think of, perform poorly, whereas our algorithm distributes food donations almost perfectly. So thank you very much, and I'm open to any questions.